All right, everybody, welcome to a new topic, organic chemistry. So, according to the IB, it's supposed to be for 12 hours. If our meetings in a weeks, we have 6 hours. So, this is probably worth of only 2 weeks, or yeah, 2 weeks, yeah, or maybe through 2 until 3 weeks. So, hopefully by um, the mid of September, we hopefully we can finish this. All right, so today we're going to start with the uh, this very bland presentation. Assessment statement is the objective. If you take a look at our website, this is supposed to be the one in the green box. This is basically the indicators or the objective that you have to understand. Like there is 10.1 introduction, 10.2 alkenes, halogenoalkenes, and reaction pathways. So there are 6 parts. So let's start with the 10.1 first, the introduction. Again, this is organic chemistry. What we are going to talk about in here, mostly talking about carbons. So my first tip to you, carbon is the backbones of the organic chemistry, and each of carbon atoms able to have 4 covalent bondings like that. So this is going to be useful for you later on. This is number one atoms that will be uh, discussed, carbons, and after that, of course, hydrogen. Hydrogen is able to form one covalent bond like that. Oxygen, two, nitrogen, three, like that. Other than that, will be yeah, we have halogen as well, but this is probably the 4 most common atoms that we are going to talk about in here. We basically will talk about their combination, their properties, and everything. Okay, and you are going to have a few of new terms or chemistry's vocabularies. So I think it is good thing for you while you're listening to this, you can notice several new vocabularies. Let's start with assessment statement number one from 10.1. This is describe the feature of homologue series. Homologous or homologue. This is a new term for you. Basically, this is referred to the same general formula. So this is if they have uh, the same general formula, we call them homologous. What is the meaning by that? So the difference between them is only CH2. They said they have similar chemical properties, and there is a pattern or gradation in physical properties. Okay, so basically there's a lot of type of organic chemistry, and each of the way we classify the organic compound, the way we classify the organic compound depending on the configuration of atoms. But some of them because of this classification basis, we can find that some of them having the same or similar configuration. It just the number of atoms uh, is different. So let me give you the example. In this case, let's say I have um, the example. I have this compound. Later you will know that we call this as a octane, for example. So you have CH3, CH2. Notice the way I write in here is different than it Usually we write down the chemical formula. CH3, CH2, CH2, CH3. 1, 2, 3, 4. Let's say 5. I have 5 of this. This is the first one. The second one is, let's say I have this one. Okay. So basically the number 1 and number 2, you can identify in here. They have similar pattern. Like the difference between 1 and 2 is only the amount of CH2, right? So this is CH2, what we CH3. So this is what we call it homolog to each other. So um, if we try to create the molecular formula for the compound number 1, we have 1, 2, 3, 4, 5, C5, and then H. Let's see, the H is 3 plus 2, 5, 6, 7, 8, 9, 10, 12, 13. No, that's 12. Yeah. Yeah, I think that's 12, right? So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Yeah. This one will be C4, A, 10. Okay. So clearly they are different compound, they are different molecules, but the the difference between all of them will be the number of CH2. In the first compound, you have, let's see, this one, 3 CH2, and then the second compound you only have 2 CH2. Okay, yeah. So these two are different compounds, but they are similar in terms of patterns, and the difference between them is only the amount of CH2. Hence, we call them homologous to each other or homolog to each other. The consequences is if they're homolog, they're actually kind of coming from the same race. Think about, oh, they're both are, let's say, Bataknese or Javanese. Okay, they both are Javanese, but maybe or Bataknese lah, Bataknese. But one of them is Simanjuntak and one of them is, let's say, Butar Butar. You know what I mean? They're homologous. They're um what we call it, have the same pattern. The consequences is they will have very very similar chemical properties and also physical properties. Okay, for example, the physical properties is there will be gradation. The longer the chains they have, the more carbon they have, the boiling point will be higher, for example. And the pattern is quite in order. So this is what we call it homologous. Let me give you another example of homologous. I'm going to write over here, but later on I'm going to erase this. Let's say I have um, this guy over here, and then you go this, and then you got the other one is this. Okay, so clearly you can see that these two are similar, like, but they're actually different, but there is similarities between these two, right? So let's see in here. This is the compound number 3 and this is compound number 4. Compound number 3, they have uh 3 series of CH2, and then this one is like CH2 as well, 2 CH2. So and if we try to draw the molecular formula, you have 1, 2, 3, 4, C4, and then 8. Let's say the hydrogen is 1, 2, 3, 4, 5, 6, 7, 8, 9, and 9, and then, oh, sorry, 10. Right, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yeah, 10. And then oxygen 1. This one is C. 1, 2, 3, C3. H, 3 times 2, 6, 8. And then O. So obviously there are eh, different compound. They are actually a different compound. But the difference between them is only because the number of CH2. The difference is only by CH2. So this is the meaning of homologous. Uh, this is what we call it molecular formula. Okay, when you basically write down the number of atoms for each of this component, and then the way I write it down as this is what we call it as condensed formula. Wait, let me. This is also, yeah. This one also. Those are what we call it as condensed formula. Okay, so you have now molecular formula, and there is also condensed formula. Again, that's homologous. Um, this is basically we're talking about the classification of um, organic compound. You try to know them now better, that some of the organic compound have similar structure, have similar patterns. The difference between them is only the amount of CH2, and because of that they will have similar chemical properties, and then they will have a gradation of physical properties, or yeah, the physical properties is going to, for example, boiling point will increase when you have more CH2 on it, right? But the chemical properties will be very similar. Like for example, this compound 3 and 4, both of them are actually alcohol. So later you know that we're talking about functional group, which is the very specific of the part of the compound that determine most of the chemical properties of the molecules. That's later, but for now, you know that if compounds are homologous to each other, they will have same or similar chemical properties and gradation in physical properties. Okay. Okay, that's for this part one. Describe the feature on homologous series. You have to be able to differentiate that. Okay, pause for a minute. Uh, okay, next one is predict and explain the trend in boiling point of a member of homologous. Let's say I have um, three different compound. Okay, the first one is this. Okay, okay, and then the second one is 1, 2, 3, 4, 5. Yeah, this is 1, 2. Sorry. Uh, 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 1, 2, 3, and then 4, and then the other one is, you're going to see a little bit weirdness in here. Let's say this is CH3. See, yeah, what is this? Okay. Um, wait, I think, oh yeah, sorry, this is wrong. Uh, so this is 2, 3, 4. 1, 2, 3, 4, 5. So one more. Okay, so yeah. All right. So I have a compound number one, number two, and number three. So you have to be able to predict and explain the trend in boiling point. of members of homologous series. So as you can see in here, again 1 2 3, the difference is only the CH3 in here, that they have 3 CH3. Yeah, this is 2 CH3, this is kind of 1 CH3 probably. So now uh, if the question is, among these three example of compound or molecules, which one do you think will have the um, highest boiling point, or you're going to ask the order of boiling point of these three molecules. So the principle will be is the boiling point is, you guys, um, basically when you have a liquid and you want to make them to boil, you basically, the simplest explanation for this will be this is gas and this is liquid, correct? Okay, so um, a very simple explanation is when they're in a liquid, the distance between molecule is like this, for example, and then when they are in a gas state, the distance will be much further away apart, further apart. Okay, so basically you want to increase the distance between the molecules. So that's the principle of boiling. Okay, so again, when you boil a liquid, the simplest explanation will be you try to make the distance further apart. The effect of making the distance further apart is the interaction between molecule will be less. So interaction between molecule will be less and less, and until in gas state, they basically do not have interaction to each other. Well, they basically have, but it's very small. So again, when you try to boil them by increasing the what we call it, temperature, you basically increasing the kinetic energy of these particles, and then the kinetic energy meaning the vibration, the translation, they're basically more random and more random, and that will break the interaction between this molecule, because basically when molecule is close to each other, there is the interaction. When you learn about bonding, intermolecular forces, we have hydrogen bond, we have um, what call it, London dispersion, if you still remember. So like hydrogen dipole, if you still remember. So basically, like one of them has positive charge partially and the other is negative. So basically, will attract to each other. The closer they get, the stronger interaction will be. The farther apart they have, they will have weaker. Why my Siri is always on? I don't ask you to be on. Oh, okay, sorry. Okay, again, uh, if the distance is closer to each other, the stronger intermolecular forces will be. Okay, I mean the effect of this will be stronger. Now, if they are further apart, they basically later on will have, at some point they will break the interaction and they become gas. So that's what happened. So basically, if you want to make the distance further apart, what you need to do is break down this interaction, right? So the energy that you will give to them, like in the term of heat, will be used to increase the kinetic energy in here of the molecule. So they will move more randomly, and then it will suddenly get farther and farther apart, and then the interaction will break. Okay, so then when you want to when you want to boil liquid, you have to fight against the intermolecular forces. Intermolecular forces of, for example, London dispersion force, London force, is determined by the molecular mass of the molecules. So the bigger the molecular mass, then the more electrons in the structure, the more charge in it, and then the more interaction between one of them. So if you have higher molecular weight or molecular mass of a molecule, they will have stronger London force. Hence, you will have uh, you will need more energy to break the interaction among the molecules. Hence, the boiling point will be higher. So number one of this boiling point will be the more the more weight or the more mass, that will be higher boiling point. Okay, boiling temperature, TB, something like that. That's because of London dispersion force. Okay, so according to this principle, if you take a look at the compound 1, 2, and 3, 1 and 2, they have the same molecular formula. Sorry, 1 and 3. So let's see the molecular formula here is C 1, 2, 3, 4, 5, C5, H I think 12 supposed to be, yes. This one is C 1, 2, 3, 4, 4, H is 10. This one is C5 also 1, 2, 3, 4, 5, and then the hydrogen will be 6, 12. Okay. Now, obviously, number 1 and number 3, they have same molecular forces. According to the knowledge that we have right now, they're supposed to be having the same boiling point, but wait. But the a more obvious one is the compound number 2. They have less or the least molecular forces. The number of carbon is only 4, right? So if you calculate the molar mass of this number 2, they will be less than number 1 and number 3 because they have more, simply they have more CH2. If they have more CH2, they will have more mass, hence higher TB. So for now, we can sure that the compound number 3 will be having the lowest boiling point. Hopefully you got that. Lowest boiling point is the number 2. Okay, next one, what about number 1 and number 3? So to analyze number 1 and number 3, you have to, let me introduce you to what we call it structural formula. This one, yeah. Structural formula meaning you try to show all bondings in the compound itself, okay? So the way you are going to do this is using, if you remember, okay, carbon is always have 4 bonding, hydrogen is 1. So follow that principle. The compound number 1, first of all, you have carbon. So write it down as carbon. Carbon must have 4 bonding, right? So let's see this compound number 1. Carbon, this carbon have, write it down, carbon with 4 arms of bonding. Now they have after that got bonding with 3 of hydrogen, right? So you go 3 of hydrogen. Okay. Now this is hydrogen, yeah, not N. This is all hydrogen. And then the remaining, this one will go to the next one, this carbon. Then okay, you have carbon, and again write it down 4. Okay, write it down 4 arms in there. And then there are 2 hydrogen. Practice this together with me. So I'm writing down this second carbon and these 2 hydrogen. Okay, and then the remaining will be to the next bonding, which is the third carbon. Oh, sorry, the third carbon, this one. And then again write it down 4 arms, and then you go, okay, I need two. There are two hydrogen in there, so hydrogen, and then carbon is in there, and then you go, okay, this carbon, and then again write it down 4 arms of bonding, and then you have 2 hydrogen, and then 2 hydrogen, and then the remaining is carbon again, and then again this one, this carbon, the last one. Okay, and then you got three, sorry, just write it down 4 arms, and then 3 of them will be these 3 hydrogen. Okay, this is what we call it structural formula. Maybe take your time now to redo what I've just done. Do the practice, okay? Okay, now the compound number 3. Let's see. Let me change the color of my things in here. Okay, can I somehow? No, you cannot. Okay, the compound number 3. Now, this is a little bit. Whenever you have this bracket, it means this bracket will go to the got bonding to the. If the bracket is in at the end, that means this is going to be attached to the next carbon. So we start from here then. bracket will be following this. Okay, so again, if you have this bracket, mean you have two CH2 attached to this carbon. Okay, so you have this carbon, the blue one, and again draw four arms like that. Okay, and then they have CH3. So CH3, two of them got attached. Okay, so CH3. Okay, well, that's very weird. This is CH3 also. Now, this carbon also have hydrogen, this hydrogen. Okay, hydrogen. And then the remaining will be to the next carbon, this one. So this carbon, okay. And then again, draw four arms like that. And then you have two hydrogen like that. So okay, this is two hydrogen, and then the remaining will be to the next carbon. Okay, and then again draw four arms again, and then you have three hydrogen. So hydrogen, hydrogen, and hydrogen. Okay. Okay, now take a look at the difference between these two structures. This is what we do is structural formula, yeah. So the change of carbon-carbon is this one is carbon-carbon. Only there is one change. But the third is there is this change, and then there is this one. Sorry, this change, and then suddenly there is this branch. So this is what we call it a branch of carbon. Branching meaning you have carbon attached to this main chains. Okay, this is the main chains, like the carbon 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 chains. This one is also carbon 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 chains. It's just kind of in a straight line, even though that's not quite accurate, but suddenly there is this additional in here. So the presence of branches like that. Okay, so you imagine these branches basically will be kind of barrier for two molecule of this to get closer. Let me draw one more structure of that. So you have this. Oh, you cannot quite see this here. So let me draw the second molecules of this compound number 3. You have this, you have that, you have that, you have that. Remember, this is the neighboring molecules, yeah. So they cannot get too close to each other because there is this branch of carbon will kind of be a barrier or a what we call it, yeah, a barrier. So these two cannot get too close to each other because there is this. But if you imagine this one, the one that without branches, there is nothing between these two. For example, I draw the second structure of this compound. There is nothing, no carbon between these two, so these two can get closer together. So branch in a structure will be a barrier for these molecules to get closer. It means, remember, the distance relate to the strength of the intermolecular forces. Cannot if they can't get closer together, the intermolecular forces will be weaker. So between the compound 1 and compound 3, or molecule 1 and molecule 3, because molecule 3 has branch on it, the intermolecular will be slightly weaker because of this branch. Because the intermolecular forces is weaker, then it is easier for us to boil the compound 3 than compound 1 again. So according to this, we have the second principle of boiling point. After the molecular mass, number one is you need to find out the branches. If they has more branch, then the molecular forces will be weaker. It means if there's just straight chains, there is no branch in there, they will have higher boiling point. If the more branch they have, the lower boiling point will be. So in this case, the one that will has higher boiling point will be compound number 1. The one that will be the second highest will be compound number 3. And then the lowest will be number 2. Yeah, try to understand it. I'll give you another example after this. Okay, so let's have another example in here. Question number 8, yeah. Question number 8, which compound has the lowest boiling point? Okay, the lowest boiling point, if you want to have lowest boiling point, meaning you want to have the one that has lowest uh, molar mass or molecular mass, and you also want them to have the most branch. Okay, the most branch. Now, the easiest way to identify branch is by seeing the brackets. Look, first of all, let's see. This is 1, 2, 3, 4, 5. This is C5. This is also C. This is 4 plus 1, C5 as well. Yeah, kan? This is C4 and then plus 1 in here, so C5 as well. And then this one is 1, 2, 3, 4, 5. That's also C5. This one is 1, 2, 3, 4, C4, but there is also oxygens. So they approximately have the same molecular mass. Okay, this is example of good or bad questions, but all of them having the same among the same molar mass if you can calculate one by one. Now, the things is we have to find the branch. So the easiest way to find the branch is by find the bracket. If there is more bracket in there, then there will be more branch. This is bracket only one. This bracket, there are four of them. This is no bracket at all. This is no bracket at all. So the lowest boiling point will be C, the one that has more bracket, meaning more most branch. Let's see the answer key. Hopefully this is correct. This is number 8, yeah? Number 8, number 8, number 8, number 8, number 8. Hey, 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 number 8. Mm, that's so many things. Number 8 is B. What was our answer again? Number 8? The answer key is B, yeah? Our answer is B or not? Let me see again. I forgot. Hmm. Number 8 is supposed to be... Mana the number 8? Yeah, our answer is also B. See? Easy breezy. Easy breezy. First, find the molar mass by just the number of carbons and then see the branches itself. Okay, we have covered now this one is covered the describe the feature blah blah blah. This is already, yeah. Homologous. Wait, why cannot be annotate? This is already and this is already. Now the third one. Distinguish between empirical, molecular, and structural formula. Okay, here's the thing. The This is a very very typical of organic compound. To express or to write, to draw a molecules of organic compound, we use different possible ways to do that. Okay, so just now I introduced you to what we call it as a structural formula, condensed formula. We also have many of others. In this objective, you only need to understand empirical, molecular, and structural. But there is also other, we call it skeletal formula. Yeah, skeletal formula. So this is a different way to draw or to show, to write down an organic compound. Okay, an organic compound. We do this difference. Let's take a look at this TO Kelling. The use of different formulas illustrate the value of different models with different depths of detail. Oh, yes, exactly. So what we are doing in here is try to write down something that we can see. So we try to model it to be easier for us to understand. However, because the dimension of knowledge is so many things, sometimes we want to get better understanding on the dimension of a number of atom. Sometimes we want to just to know the angle. Sometimes we want to know the bonding. Sometimes we want to know. Sometimes we don't care about the bonding at all. We just want to know the number of atom. So that's the different depth of dimension that we want to understand will determine a what is the proper models that we have to show. Okay, so I just showed to you that in order to find out the branches, the best way to do it is to draw the structural formula, because the branch of the structure is related to the bonding itself, and the bonding can be shown in structural formula. So that's why if you want to see the branches, then you use structural formula or condensed formula. Yeah? For example, this guy over here, this example, they have one, two, three, four, five, six. They have six carbon and 14 hydrogen. Six carbon and 14 hydrogen. Okay, so this one, what we call it as a molecular formula. Okay, molecular formula. Molecular formula showing the number of atom for each of the molecules. There is also empirical formula, which is the simplest ratio. So this 6 to 14, we can get it down to, let's see, 6 divided by 3 is 62. 14 divided by 3 cannot. So not 3 then. So maybe divided by 2. Divided by 2, this is 3H7. Okay, so this is the simplest ratio between the atom in there. This is what we call it empirical formula. Empirical formula. Okay, ya. Molecular formula showing the actual number of carbon and hydrogen in it. Empirical formula does not give you an actual amount of carbons and hydrogen, but it will give you the same ratio as the molecular formula. The ratio is 3 to 7. 6 to 14 is also 3 to 7, right? So I think when you learn about stoichiometry, you learn about this one, molecular and empirical formula. But usually we write down molecule only using this way. This is going to be applied for other or inorganic compound. Inorganic compound, that's what we have, molecular and empirical formula. Okay, but then in organic chemistry, sometimes the case that we just have, when we want to analyze the boiling point of homologous, like pattern of boiling point of homologous series, you can only relay rely on this molecular formula. You have to know the branches. And as you can see in here, there is no way you can see the branches in this molecular formula. No, no, nothing in there. C6 it's 14. You don't know this is have branch or not, right? They're only showing to you the number of atom. That's why when we do this uh, okay, when we do this analysis of physical properties, like let's say boiling point, we need to have better models. The models that we want to use is what we call it structural formula. Okay, that's why, okay, structural formula, because C6H14, you can draw the structure like this, just a straight one, 1, 2, 3, 4, 5, and 6. But you can also draw it as this. For example, this is 1, 2, 3, 4, and then one of them is branch, or maybe, okay, four but two of them is branches. Okay, so in this case, modeling of structural formula showing all the bonding. I don't draw hydrogen, by the way. You just need to add hydrogen for each of these, and I'll guarantee you all will be just H14. Try by yourself. Just add all the remaining bonding in here with hydrogen. Yeah, remember, carbon have to have four bonding. This structure number 1, 2, and 3, this we call it structural formula. When you want to see we call it the bonding inside the compound itself, and that will be useful in organic chemistry to later on determine the boiling point. Okay, so again, be careful, sorry, please understand the difference between this is a structural formula, this one is structural formula, and this is empirical formula, and this is molecular formula. Now, yeah, more sure, structural formula is useful to us. But then again, imagine you want to write a document, right? Like you want to type a Google Docs. Like, oh my God, how to write this down in Google Docs, right? How to type it? Like you have to show the drawing and blah blah blah. That's not going to be practical. What I mean. by this is not, yeah, it's gonna be difficult lah. You know what I mean? Like again, the positive things about the structural formula for sure, yeah, it's going to show you the bonding means you're going to have more information about this particular compound, but nah, it's not practical if you want to use it as a like Google Docs or something. Just document. So to bridge these two, we have condensed formula. This is condensed formula. Condensed structural formula. Okay. The condensed structural formula is basically it's the solution. So it will show to you the idea of the bonding. Like if you want to know the branches, you can also find out the branches. But it's not as fancy as the structural formula, so it's still possible for you to draw it in like Google Doc or something. So the way we do it is, for example, like okay, let's see, I wanna convert this structural formula, this one, into condensed formula. Okay, how we're going to do this? Okay, let's see. Let's erase this. You understand lah, molecular formula, empirical formula. Okay, yeah. So I erase this. If not, then just play back. Okay. Let me pause first so you can I can erase this is faster. Okay, right now let's convert this structural formula into um, uh, condensed formula, condensed structural formula. So this is carbon number 1, 2, 3, 4, 1, 2, 3, 4, 5, and 6. Okay, so carbon number 1. Okay, so let's see in here, carbon number 1 have 3 hydrogen attached to it. Okay, so CH3. And then the next one is carbon number 2. See, carbon number 2. Okay, carbon number 2 has 2 hydrogen attached to it. So 2 hydrogen attached to it. Carbon number 3. Carbon number 3. Another 2 hydrogen. This one, yeah. And then carbon number 4 and number 5 the same. So number 4 and number 5. Now number 6, they have 3 hydrogen. See, this is the way you can write down. So that way you can easily write it down in Google Docs or you type it in Microsoft Word or something. This is condensed formula. This is easy level because there is no branches in there, so you can just write it down like that. Let's move to another example, but my suggestion is just repeat again this video on the part when I convert this structural to condense, yeah. But I'm now going to moving on to the more challenging case. Okay, now, yeah, I know the drawing is not that good, but it's okay. let's let's try to convert this structural formula into condensed formula. This is C number 1, number 2, number 3, number 4, and number 5. So again, start with C number 1, yeah. Oh, sorry, C number 1. They have 3 hydrogen, right? This one. So CH3. And then C number 2. Okay, C number 2. They have 1 hydrogen and 1 CH3. Okay, so you go CH and then bracket CH3. That's the way you do this. And then you go C number 3. C number 3, you will have 1 CH3 and then 1 hydrogen again. So okay, C again and then hydrogen again, this hydrogen. Okay, and then bracket this CH3. So bracket CH3. Now C number 4, remember this is C number 1, okay, this is C number 2, this is C number 3. Now C number 4. C number 4, they have 2 hydrogens, so directly CH2. Now C number 5 has 3, CH3. Yeah. So that's the way. Obviously, this need more practice, you guys, but I think you have the idea. Now, another thing about condensed formula, the reason being we call them condensed, we literally try as much as we can to condense them into simplest way to do it. So this is, yes, condensed formula, but the better way to do this is take a look at the number of CH2 in here. CH2, 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 CH2. 4 times of CH2, so they go CH2 4 times and then CH3. Okay, that's empirical formula, molecular formula, structural formula, and condensed structural formula. So you have four things, yeah? Empirical, molecular, structural, and condensed structural. Four things. One other, we call it skeletal formula. Go ahead, find Google what skeletal formula is. Okay, next up we have Uh, describe structural isomer as compounds with the same molecular formula but with different arrangement of atoms. Yeah. Another new vocabulary for you. Isomer. Isomers. What is isomers? This is a very popular terms in organic chemistry. Um, Again, this is because carbon is very, very flexible in terms of bonding. So the same, let's say, if you draw, if you have, let's for example, C5, 8, 12, the molecular formula of a molecules C5, 8, 12, you're basically able to draw one more than one possibility of structural formula. Okay, this is number one possibility. The hydrogen just follow ya guys. I mean hydrogen is 12. Okay lah. Let me draw hydrogen, 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 hydrogen. Let me skip this. Skip forward and voila, you have this first structure. The second possible structure, let's put branch on it. So one, two, three, four, and one of them is here. So still five, and if you add hydrogen in it, hydrogen, remember yeah, carbon has to have four bonding. Hydrogen, hydrogen, so this is need three more. So hydrogen, 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 and hydrogen, and hydrogen, hydrogen. Okay. Okay, so this is still, if you count it, it's still C5 and H12. Okay. The third possibility, let's see, one, two, three, and you have this carbon and this carbon again. So just add hydrogen lah. You believe me lah. One, two, three, four, five. Yeah. So this is three possibility of structural formula, different structural formula form from the same exact molecular formula. So this compound number one, number two, number three, we call they are actually isomers to each other. So that is what the meaning of isomers. Isomers is compound that have the same molecular formula but different structural formula. Again, isomers is a compound that has same molecular formula, but they have different structural formula, meaning the arrangement of them, arrangement of atom here, arrangements of atoms are different. Okay, there are this the rest of we just finished this, yeah, we just finished this. Oh, sorry, just finished this. Now this one talking about structural formula again. I'm not going to repeat it. This is structural formulas again. This is structural formula again, but this one functional group. This is new things. Later we'll talk about there is alcohol, aldehyde, ketone, carboxylic acid, and halide. You Google it, you'll find out what is functional group of that. Later I'll show you. But for now, let's um the remaining is about naming. So this is naming IUPAC, IUPAC, IUPAC. This all is naming, 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 and naming. How to give name to this organic compound. Okay, so naming is very important, and this is one of the signs of modern chemistry. If you remember that chemistry kind of started, well, chemistry is a science, right? Experimental science. In IB it's group 4 actually, experimental science. But then back then, before became a science, chemistry is kind of pseudoscience or like magic trick things. People do weird stuff with chemistry, with yeah, in chemistry, like we call them alchemist era. In alchemist era, if you could take a look at this very wonderful website, Chem with Chris. Ooh, promotion, the sponsored by chemwithchris.com. So if you for example this one, yeah, let's just click this one. Let's just give you a background story first, a little bit, so everything will be more relaxed. Ah, the internet at my home. Okay, so take a look at this picture carefully. So there is this rainbow, and then there is also this, I don't know, dragon or something. I don't know, this weirdness of blah blah blah. So before the science era of chemistry, we call it alchemist era, the naming of the elements is not standardized. So sometimes they can call nitrogen as rainbows and sunshines, for example, like that. It's up to them. There's no standard for that. So it's going to be difficult for people to understand what they meant, because the language is not standardized. So the meaning of the language only be able to be understand by the one that write it out, write the text, yeah. And that's also one of the characteristic of non-science world. Non-science world is not quite open. So the reason being they don't standardize the language is because they want to keep the recipe of this chemistry reactions secrets, okay. They don't want people to understand how the way we can react this to become that. So that's the nature of non-science, okay. Nature of a non-science area is they don't speak the common language. They tend to keep everything at secret. But in science way, the nature of science, knowledge is belong to everyone. We understand everything is open, so the knowledge can be evaluated by everyone. You can test the hypothesis and the results supposed to be the same uh, anywhere in this God, God's grains of earth. So that's why we need a common language, a universal language for science, so people will easily understand our knowledge. Yeah. So now we need to also create a rules to give name of this organic chemistry, organic compound. So we have so then we are able to communicate to each other. I'm not going to explain now because this is already almost 1 hours of a video. Can you please try to just find out what is the rules of naming in organic compound by IUPAC? IUPAC is an international union of pure and applied chemistry. This is an organization that maybe one of their job is to give names to the compound or at least set the rules. But that's not all rainbow and butterflies as well. Giving standardized name is not always practical because the rules sometimes for the the more complicated compound, if you want to follow the rules of IUPAC, that will be really not practical. So for the complex compound, we don't use rules of that. Like we usually give them like we call it trivial names. The names is not really under the standardized of rules of IUPAC, but still common knowledge. You know what I mean? So yeah. So protein, for example, they have very big structure. Carbohydrate also. The naming of them is not really, it's not practical to follow the IUPAC rules. So go ahead. After this, you have probably 30 more minutes or 40 more minutes because you have two periods. So you can, first of all, I want you to make a note uh, on the one that I explained to you. And if you can list down questions, that will be better. And if you still have time, go ahead, Google the IUPAC rules of naming of organic compounds. Good luck, you guys. Thank you very much. Bye bye.